right, guys. Today we're going to talk about triple integrals and cylindrical and spherical coordinates, and we're going to talk about vector fields. So we have our conversions, cylindrical conversions. Remember, cylindrical is just polar in 3 dimensions. That is, the x, the y, are the same equations as polar, and then z equals z, because whoever thought of this was lazy. No, I'm kidding. Z equals z is the conversion for z, so you don't have to really worry anything about that right there. And then we also have r squared is equal to x squared plus y squared, but we already knew that. That was the Pythagorean theorem. You know, tangent of theta equals y over x. We knew that from trigonometry. If you look at x equals r cosine theta, that is x over r equals cosine theta. We knew that from trigonometry, and same thing with y over r equals sine theta. So in the integral, if we have the integral over e of f of xyz dv, this is the same thing as the triple integral of f of r cosine theta, right, because that's a conversion for x, r sine theta, because that's a conversion for y, comma z, because that's a conversion for z. Our dv, it's converted to r dz dr d theta, and when e is the general region bounded by, well, let's see, e in this case would be all points r theta z, such that, okay, now d lies in between u1 and u2, which can be, you know, up to functions of r and theta. So z is less than or equal to 1, or greater than or equal to u1, z is less than or equal to u2. R is in between a function, 2 functions of theta, but again, it can be constant. h1 of theta, h2 of theta, and theta, it's like our, you know, independent variable, lie in between alpha and beta. Remember, theta, the you know, proper range of values for theta is in between, you know, 0 and 2 pi. And for r is a radius, a distance, so it's greater than or equal to 0. Okay, so let us look at this example from Stewart's Calculus book, page 1031, number 16. Sketch the solid and evaluate. Now remember, this is the equivalent of dv, so our function that we're integrating up to is 1. Thus, the what this triple integral calculates is really volume. So let us sketch the region. What is this region? So we have r is equal to x squared, the square root of x squared plus y squared. When we know r squared is equal to x squared plus y squared. So r is equal to the square root of x squared plus y squared. Okay? But this is z equals r. So we're integrating from 0, from z equals 0, to z equals the square root of x squared plus y squared. That is to say, z squared is equal to x squared plus y squared. Theta, in this case, you can see 0 to 2 pi. That is one full revolution about the xy plane, around the xy plane from the positive x-axis. We see r is from 0 to 2. So r goes from 0 to 2. So we know what this is from conic sections. What is it? It's a cone. It's a cone. Remember, when we have z squared equals x squared plus y squared, or some constants times x squared plus y squared, then we have a cone. When we have z by itself equals x squared plus y squared, well, then that is a paraboloid. But this is a cone. So let's go ahead and sketch what this solid looks like. Okay. Well, the radius, that's the distance from the origin on the xy plane, is going from 0 to 2. We have 2's out here. We have a positive 2, a positive 2. Remember, this is x. This is y, negative x, negative 2, negative y, negative 2. Okay. And then we're going all the way around. We're going all, oops. I don't know how that happened. Oh no. Technical difficulties. Here we go. Cool. All right. So we're going, all the way around. So this would be the impression left on the xy plane. Then we're going up to this cone. So the solid we're finding the volume of is below the cone, above the xy plane. So it's a cylinder with a cone cut out of the middle. Solid cylinder with a cone cut out of the middle. Okay. So we can go ahead and evaluate this. Let's see. We have the integral of r dz d theta dr 0 to r 0 to 2 pi 0 to 2. Okay, so we integrate z. Well, the integral of 1 is just z. The integral of 1 times r is zr. So we have the double integral from 0 to 2 pi, from 0 to 2, of z times r, evaluated from z equals 0 to z equals r, d theta dr, and then this turns out to be integral from 0 to 2, 0 to 2 pi. Plugging in z is 0 and z is r, we get r squared minus 0 d theta dr. Okay, well, this, we have constant bounds, and the integrand is a function of r separately and theta separately. The function of theta being 1. So I can separate this integral into two different integrals, multiply them. Okay, so we have the integral from 0 to 2 pi d theta times the integral from 0 to 2 r squared dr. Okay, the integral of 1 theta d theta is just theta, so we get theta, plug in 2 pi minus 0 is just 2 pi. Then we get multiplied by r cubed over 3, evaluated from 0 to 2. Plugging in 2, we get 8. That's 8 times 2, which is 16. So we get 16 pi over 3 minus 0. page 1031, number 15. Sketch and evaluate, the same instructions. So remember, we're calculating volume again because this is r dz dr d theta. Because, 1 dv is equal to r various combinations of dz, dr, and d theta. Okay, so r squared is equal to x squared plus y squared. And that's our z bound, right? So we're going from 0, z is equal to x squared plus y squared, aka r squared. But z equals x squared plus y squared is a paraboloid centered at the origin. Okay, and then r, well, we have the same r as last time from 0 to 2. But this time our theta is different. We're going from negative pi over 2 to pi over 2. So if we look at this on the xy plane, okay, we have negative pi over 2 right here with, radius 2. Positive pi over 2 with radius 2. Angle 0, radius 2. So this is the portion of the xy plane we are integrating from. And so what does this look like in R3? Well, we have, let's see, hopefully that will work. Okay, so we have, let's see, from negative pi over 2 to pi over 2 on our theta bounds. So that would go from our negative y to our positive y through positive x. So here is point 2, 0. Here's a point 0, negative 2. Here's the point 0, 2. And then this is the region I just drew, just in R3 now. And we're integrating from 0 to r squared. Remember, r squared is a paraboloid. Okay? So, when we have, how high does this paraboloid go? If we plug in, any point along this curve in R2 into our function z equals x squared plus y squared, we're going to get a value of 4. So our paraboloid goes up 4 units, and we have a paraboloid. And so I kind of drew this a little bit too far away, but we have finding the area. It's like a solid cylinder, except you took an ice cream scoop out of it because it's, like a paraboloid shape, curvy, not like last time where we had a solid cylinder minus this cone. It's now a solid cylinder minus this paraboloid. So we integrate from 0 up to the paraboloid, r going from 0 to 2, and theta going from negative pi over 2 to pi over 2. So it's half of it. Okay, so we can go ahead and integrate. We have the triple integral, 0, r squared, r dz dr d theta, r going from 0 to 2, theta going from negative pi over 2 to pi over 2. Integrate 1 r with respect to z, we get zr. Zr evaluated from 0 to r squared, dr d theta, 0 to 2, negative pi over 2 to pi over 2 and theta. Okay. Plugging in r squared for z and then 0 for z, we're going to get r cubed minus 0 dr d theta. They were evaluated from 0 to 2, negative pi over 2, pi over 2. Okay. Now we add 1 to the exponent, divide by that number. So we do r to the 4th over 4, divided from 0 to 2. And then this is two separate functions. This is, r times 1. We get theta 1 as the function of theta. So we're multiplying this by the integral from negative pi over 2 to pi over 2 d theta. Okay. Integrating theta, we get, or integrating d theta, we get theta. So theta evaluated from negative pi over 2 to pi over 2. Then plugging in 2 for r is 2 to the 4th. Well, 2 to the 3rd is 8, so 2 to the 4th is 16. 16 divided by 4 is 4. So this is equal to, we got pi over 2 minus negative pi over 2 times 4. That's 4 pi. Looks good. Yep. Okay. This one is a little bit more complicated. Okay. So we have this region E given in rectangular coordinates. Now we must convert to cylindrical to evaluate this region. That's the easiest way to do this. So let's go ahead and sketch what E looks like. E is a solid within the cylinder. X squared plus y squared equals 1. So what does that tell us about R? If x squared plus y squared equals 1, then R will lie in between what two values? Zero and 1. That's perfect. Yes, you could reason it out, just looking at the picture, or you could say, okay, well, going from the origin all the way to this cylinder, then we know that r squared is equal to x squared plus y squared. That's equal to 1, so r squared equals 1. R is equal to, you take the positive because r is always positive. R is equal to 1 is our upper bound for r. Okay. So we're going from z is 0 all the way up to the cone z equals 4x squared plus 4y squared. Well, z squared is equal to 4 times x squared plus y squared is equal to 4r squared. So z is equal to, the square root of that is just 2r. So we're going from 0 to 2r on our z bounds. We already established that r is going in between 0 and 1. And now theta, obviously, is 0 and 2 pi. And now this integrand is something other than 1, so this doesn't actually calculate volume. If x squared was the density function of this solid, then this would calculate mass, because we know that what density is equal to mass over volume, which implies mass is equal to density times volume. So dV is like our volume, and then if x squared was our density function, then this would equal mass. Okay, so let's go ahead and build this cylindrical integral. Okay, so x squared in cylindrical turns into r squared cosine squared theta. So we have r squared cosine squared theta. dV turns into r dr. Let's do dz first, because this is in terms of r. We can do dr d theta. Okay, So since these in terms of r, we're going from 0. Oh, sketch the solid, yeah. So it's a paraboloid. Like that. Yep. Okay. And then the region we're doing is not inside the paraboloid, but outside the paraboloid. That. Okay. So let's go ahead and evaluate this integral. Oh wait, I need the bounds. So the 2r, r is going from 0 to 1. Theta is going from 0 to 2 pi. Okay. So this is actually we have r squared cosine squared theta, r cubed cosine squared theta, dz dr d theta, 0 to 2r, 0 to 1, 0 to 2 pi. Integrating z, there's 1z, or 1 times dz, no z's. So that's just z. And plugging in 2r, we would get the integral from 0 to 2 pi, the integral from 0 to 1, 2r to the fourth cosine squared theta dr d theta. These functions are separated by multiplication, and the bounds have no variables in them, they're constant. Thus, we can separate this out into two integrals. I'm going to pull the 2 out, the integral from 0 to 2 pi cosine squared theta d theta times 0 to 1 r to the fourth dr. Okay. To integrate this, what do we have to do? How do we integrate cosine squared theta d theta? And while I wait for an answer, yes. Yes, but what's the argument on that? The argument of cosine. The angle. What does the angle turn into? Oh, we know that, okay, so we have the power reducing formulas. This is going to be 1/2, and then you can either do times 1 or just distribute 1 through, and then this would be plus cosine of 2 theta. The angle gets doubled, and then this is the same thing minus sine. Yeah, so whatever the angle is right here gets doubled after you put it through this formula, 2 theta. Okay, so perfect. We have, but then the 1/2 we can get out. Yeah, the 1/2 can get pulled out, and then that cancels with the 2. So you got the integral from 0 to 2 pi, 1 plus cosine 2 theta, d theta. We haven't integrated yet, times r to the fifth over 5, evaluated from 0 to 1. Integrating 1 d theta, we get theta, and this is plus sine of 2 theta over 2, evaluated from 0 to 2 pi, times 1/5 minus 0 is just 1/5. So we get, plugging in 2 pi, we get 2 pi, and then sine of 4 pi is just 0. Plugging in 0 zeroes everything out. So we get 2 pi times 1 over 5, or 2 pi over 5. Uh-oh. Oh, I did this wrong. Yeah, 2 pi over 5, here we go. That was it. Yeah, 2 pi over 5, sweet. Okay, so to recap over cylindrical, we have our conversions. And then, dV magically at this point, because I guess I got it out of the curriculum, turns into r dz dr d theta, and then we make the proper substitutions in the integral. For every x, we put r cosine. For every y, we put r sine. For every z, z stays. And we have our conversion here. So we can go on to cylindrical coordinates, or spherical coordinates. Triple integral and spherical coordinates. We covered this the first couple weeks of class. So rho is distance from the origin. But it's a different distance from the origin than r, because r was a distance from the origin on the xy plane. Rho is the distance from the origin in 3D space. And we can see that by rho squared equaling x squared plus y squared, because this is rho is equal to the square root of x minus 0 squared plus y minus 0 squared plus z minus 0 squared. If x, y, z is a point, then this is the distance from the origin, being rho. Theta is the same theta, 0 to 2 pi. And then remember, phi is in between 0 and pi. And it's the measure from the positive z-axis downward. So if we have x, y, z, you would start counting phi from up here, and then you just go down until you get to the negative z-axis, because that would be pi, angle of pi, from the positive z to the negative z. Okay. And so f of the triple integral over e of f of x, y, z dv turns into this animal. Notice instead of r, we have rho squared sine phi is converted from our dv. Now, if you want to find out where this comes from, I'm going to forward you to chapter 15.10, change of variables. Doesn't look like it's on the curriculum, which is unfortunate, but I guess that's the COVID decision. So anyways, an E, this would be a spherical rectangle. Okay. So we can look at an example. Okay, so E lies between two spheres. We're integrating x squared plus y squared dv. So we can do this no problem. If we had a picture, it would look like this. This is distance 2 from the origin. This is distance 3 from the origin. And then it's the area or the volume between these is what we're integrating over. This triple integral doesn't calculate volume because this is something other than 1. So no volume. It would be a mass if this was a density function. Okay. So if x squared plus y squared equals 4 and x squared plus y squared equals 9 is the region we are integrating over, and that's rho squared equal to rho squared equals 9. Well, that's just rho lies in between 2 and 3. Now to get our theta bounds, we look at the picture. Well, we're just going all the way around. So theta lies in between 0 and 2 pi, and phi lies in between 0 and pi. All of the part of the sphere that's been cut out in the middle, all of it. So this accounts for cutting out the middle, distance between 1 and 2, and then this accounts for, well, we're going all the way around both ways. Okay, so we have the triple integral over E x squared would be rho squared cosine squared theta sine squared phi. Y squared would be rho squared sine squared theta sine squared phi. Multiply by our dv. dv is rho squared sine phi. And then we're going to multiply by, we can do d rho, d theta, d phi. Okay, where rho lies in between 2 and 3, theta lies in between 0 and 2 pi, and phi lies in between 0 and pi. Okay, so we can factor out a rho squared sine squared phi from the integrand. So we have rho squared sine squared phi times cosine squared theta plus sine squared theta times rho squared sine phi d rho d theta d phi. 2 to 3, 0 to 2 pi, 0 to 2, 0 to pi. Well, cosine squared plus sine squared is just 1. So then we get rho to the 4th sine cubed phi d rho. I did that backwards. D rho d theta d phi. Okay, and we're evaluating from 2 to 3, 0 to 2 pi, 0 to pi. Okay, so these, we can separate this into 3 integrals. We have the integral from 0 to pi, sine cubed phi d phi times 0 to pi, 2 pi d theta times 2 to 3 rho to the 4th d rho. Okay, well this middle one, that's just 2 pi. This one, this is going to be rho to the 5th over 5. But how do we integrate sine cubed? How do we integrate sine cubed? And then this would be rho to the 5th over 5. So this would be 3 to the 5th minus 2 to the 5th over 5. Yeah. I call it peeling off. Isolate sine squared and sine. Convert sine squared to 1 minus cosine 2 theta over 2. Oh, let's try that. So we're going to peel it off or isolate. So we have sine squared phi times sine theta, or sine phi d phi, 0 to pi. Okay, so let's convert this to, say, 1/2 minus cosine 2 phi over 2 sine phi d phi, 0 to pi. Now what do we do? Distribute the sign and do u substitution. Yeah, the theta and the 2 theta. So if we distribute, we can integrate the first one. We have 1/2 sine phi, that's easy. Then we would have cosine 2 theta, or 2 phi, excuse me, sine phi over 2 d phi. Yeah, then it gets to the point where, like, okay, our arguments are different. So I couldn't do a u substitution if I picked u to be sine. Well, my du wouldn't match up to cosine. that doesn't work. So if we chose u to be cosine 2 phi, well, then my du would be sine 2 theta, which we don't have. So this is actually not the proper way, unfortunately. But good try. So yeah, when we have, but the first step was good. You're good. It's a learning experience, right? That's when I do integrals, like just entertaining the idea is good because you see why it doesn't work, and then we can learn from that. So this doesn't work because I convert the sine squared phi into the power reducing formula. My angle doubled, and then doubling the angle, we can't use u substitution. There's actually, and it makes sense why you thought that too, because we had just used double angle. But there's an even easier one, more natural trig identity. Can we think of one? Integration by parts. Yeah, no, think of a identity, trig identity. That's right. Yep. We're going to do sine squared theta plus cosine squared theta equals 1. Isolate sine squared to get 1 minus cosine squared theta. Yeah, that is always how you should do these higher power trig integrals. Actually, as a matter of fact, this type of integral, the integral sine to the m, I'll call it phi. Why not? Cosine to the n phi d phi. This type of integral is covered. I can find it. I think it's chapter 7.2 in Stewart's calculus book. It was in integral calculus. I don't know. Oh, you probably took math 2414 since you're in this class. So yeah, in 2414, it's covered. It's trigonometric integrals. And it's chapter 7.2. You can also do secant to the mx, tangent to the nx, dx. And yeah, so the whole process of this is you peel off 1 as a proper first step, and then you convert the rest using Pythagorean identity. And after that, it's just a nice u substitution. So we have sine squared phi plus cosine squared phi equals 1. That is cosine squared phi equals 1 minus sine squared phi. I did that backwards, didn't I? Okay. Well, we know that the sine squared phi equals 1 minus cosine squared phi. Yes. So we have 1 minus cosine squared phi times sine phi d phi, integral from 0 to pi. What do I do now? Let's see. I think I didn't distribute. Yeah, you don't have to distribute. You can just do you can for sure, but I'm not going to. Be less work. Just U sub. Yeah, just U sub. What do you pick for U? Cosine squared? I choose U to be cosine squared. Du would be 2 negative cosine phi sine phi d phi, which we don't have. Pick a more simple U. Pick cosine. And then this would be U squared right here. And then the reason why you pick only this for U is because du, yeah. So du now is negative sine phi d phi, or negative du is equal to sine phi d phi. And I like to convert my bounds. You don't have to. You can resubstitute at the end, but I'm going to. So our phi goes in between 0 and pi. So u would go in between 1 and negative 1. Okay. In that order. So we have from 1 to negative 1, 1 minus u squared times negative du. Okay, well, these bounds are backwards. How do we account for that? Yeah, exactly. Yeah, we have a negative sign right here. And then remember that the integral from a to b of f of x dx is equal to the negative integral from b to a of f of x dx. So yeah, that works out perfect for us. We can flip this, negative 1 to 1, and flip this constant would be pulled out front, and then that would turn positive with this one. And so we have 1 minus u squared du. Okay, so this integrates to u minus u cubed over 3, evaluated from negative 1 to positive 1. So we have 1 minus 1/3 minus negative 1 minus negative 1/3 plus 1/3. So this turns into 1 plus 1 minus 1/3 minus 1/3. This is 2 minus 2/3. This is over 3. 6 minus 2, so this is 4 over 3. Yeah, the integral is 4 over 3. And then we're multiplying by this animal right here. 2 pi, 3 to the 5th minus 2 to the 5th over 5. And we get some really big number. So we get 4 over 3 times 2 pi times 3 to the 5th minus 2 to the 5th over 5. And so I'm going to use a calculator for this one. 3 to the 5th minus 2 to the 5th is 211, and times 8, because that's 2 times 4. So we get 1688 pi over 15. Now this number is so big because, one, we had an integrand. It's not just volume. We're integrating a positive density function over, and then this is just a big region. The volume between these two spheres is quite large. And so yeah, and one thing else that I'll talk about, so I was looking at the homework, and it was something along the lines of, we had the region being between x squared plus y squared and the square root of 3x squared plus 3y squared. Okay. So this is the square root of 3 times the square root of x squared plus y squared. These are cones, okay? These are cones. And so we have less steep cone, we have a more steep cone. So what this will look like, you're not going to be integrating from 0 to some height like we have been doing. Rather, you'll be integrating from lower cone to upper cone, like that. The more steep one, the sharper angle, is the root 3, and then the lower one is the less steep, the square root x squared plus y squared. So I just wanted to say that because from last week's homework we had triple integrals and rectangular, where it was a pretty crazy region. What I think was happening was we had like we had like plane. I was going like this. It was independent of x, and then we had another plane like this, independent of y, and then it like flipped. It like at a certain, I think it was at like this line. At first, this one was lower, and then this one was upper. But then on this side, on this region, we had this one being lower, and then this one being upper. So I just wanted to kind of clarify, give you a little bit of a hint maybe. Okay. So yeah, that was spherical coordinates. So let's go ahead and talk about vector fields. Have you guys gotten to this in class yet? Let me see. No. Okay. Well, yeah, these aren't too bad. This is chapter 16.1. And actually it'll be covered I think tomorrow. Yeah, the 3rd. Oh wait. It says Tuesday, November 3rd, vector fields and line integrals. So that's strange. I guess maybe y'all have fallen behind in class on the schedule. Anyways, we can go ahead and talk about it because it will be covered. So a vector field, we've already kind of dealt with some of these. Remember the gradient of a function. The gradient of a function is a special vector field. So now we're talking in more general terms. A vector field is a type of function. So let D be a subset of R2. A vector field on R2 is a function that maps each point in D to a vector in R2. So the domain, okay, so we have F. We denote it capital F, and I use the vector notation as a hat. So this new function, capital F, maps points from R2 to vectors in R2, or points in R3 to vectors in R3, or points in Rn to vectors in Rn. Which, let's see. Yeah. So I guess I wrote this example out, but I didn't give any instructions on what to do with it. Sketch. And there's one like this in your homework, but they have it in 3 dimensions. This is the same vector field, only in 2 dimensions. This is, I think, for homework 11. It's essentially the same vector field. It's a plus or minus sign or whatever. Okay, so F maps R2 to R2 given by f of xy equals negative y comma x. So how do you sketch this? I'll show you. We our input is a point in R2, so we're gonna have xy. Oops. Yeah, point xy, and then make a table x, y, f of xy equals negative y comma x. It's a vector. Okay, so we choose all combinations for x and y, or just a lot of them so you get a good picture. Start out with 0, 0. What is the output vector? Zero, 0. Negative 0, 0 turns into 0, 0. Yep. So the point 0, 0, the origin, gets mapped to the 0 vector. Cool. Now, what if we have the point 1, 0? That is right here. Starting here, what is the vector? It's 0, 1. That's right. Because negative 0 is still 0. Then we have 1. So what does this vector look like? Well, it has an x-coordinate of 1, or x-coordinate of 0. So we travel 0 in the x direction, and we travel positive 1 in the y direction. So starting at this point, we have vector going like this. Okay? What would the point 2, 0 be? By golly, you're right. 0, 2. So we can see we can see that as we travel along the positive x-axis, that was ugly. We just get vertical positive. Oh man, goofing. We get vertical positive vectors in this vector field. Okay, and then at 3 we would get 0, 3, and that would go up 3. Okay. So what about the point 1, 1? What do we get for x is 1, y is 1? Negative 1, positive 1. So x is going negative 1. So starting here, x goes negative 1, y goes positive 1. We ended up right here. Okay. What about at the point 0, 1? We get negative 1, 0. Yeah, that's right. So that would map to this. Then we can see that if we plug in 0, 2, we would get the same thing, just a larger magnitude. Okay. What about the point 1, 2? Negative 2, 1. So x is going, so that point's right here. And then we go negative 2, that's 1, 2, and then we go down 1. So it would be mapping to right here. Wait, positive 1, excuse me. So we go negative 2 in the x. Boom, boom, up 1. We go right here. Okay. So let's go ahead and do a couple more points. If we do x is negative 1, y is 0, we get 0, negative 1. So that's going to be like this. And then this one would go down twice. And then 3 would go down thrice. Okay. And so we can see what's going on with this vector field. It kind of goes in a circle. So if we do point negative 2, positive 1, what did we get? We get -1, -2. So that's -2, +1, that's right here. And then we get the vector, x goes -1, y goes -2. Like that. And then let's go ahead and do some in the fourth quadrant, or the third and the fourth. Let's plot -1, -1, xy, -yx. Get a good picture of this. So if you do -1, -1, you get +1, -1. Because y flips sign, x keeps sign. And then they switch positions. So we have at -1, -1, that's right here. We get the point, or we get the vector. X goes positive. Y goes, x goes +1, y goes -1. That. And then at the point 1, -1, we get 1, 1. That's here. We get 1, 1. Yeah. And you can fill in more spots. We have 1, -2. That would be 2, 1. 1, -2 is right here. We go 2 in the x direction, 1. Yeah. That. So. And then you can talk about what would happen if, so like imagine this is like a a whirlpool, or it's a force field, or a vector field, right? So you throw like say you throw an apple in there, or like a ball, and say it lands like, oh, I don't know, right here. And this ball would get pushed along by these vectors, and it would form a flow line, is what they call it. So it'd probably go in a circle like this. It's called a flow line. If you place a particle in this vector field, what path would it take? Okay, I'll let E be a subset of R3. A vector field F is a function that maps a point in E to a vector in R3. I already said that, but this is just, vectors, a point in R3 getting mapped to vectors in R3. And we have an example. F maps R3 to R3, given by f of xyz equals k hat. What would this vector field look like? A bed of needles. What direction are they going? Up. How long are they? What's the magnitude? 1. Yeah, that's right. This vector field is not dependent on any of the variables, so it's like autonomously at every single point. It's the only thing that it has is vectors of length 1 going up in the z direction. Because ijk, k is the unit vector in the z direction. So yeah, we would have like that, 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 just like that. They're all the same vector. Yeah. So yeah, that was a pretty nice example, pretty simple example. It's following my screen. Oh my goodness. Okay, it's gone. Yeah. So plot the gradient vector. Oh, I already did it, but okay, let's erase this. Okay. Yeah. Plot the gradient vector field for f maps R3 to R3. No, this is f maps R3 to R because we have a scalar output gradient. So yeah, we get a number as an output. This function maps a point in R3 to a number given by the square root of x squared plus y squared plus z squared. Remember that the gradient vector is given by f sub x, f sub y, f sub z, if f maps R3 to R. And so we have del f maps now R3 to R3 given by, and then we calculate del f. Well, the partial derivative of f with respect to x, f sub x, would be 1/2 x squared plus y squared plus z squared, the negative 1/2 times 2x. This is x over the square root of x squared plus y squared plus z squared. Then you would get the same thing for y and z, except you would have a y and a z in the numerator. So you can actually write this in a compact form. You can write it x component divided by magnitude of vector x. Because remember, magnitude of vector x, if x is in R3, is the square root of x squared plus y squared plus z squared. So this would be an acceptable answer. Y over magnitude of x, z over magnitude of x. Let me ask, what happens to the size of these components, what happens to the size of these vectors as it moves away from the origin? So we're dividing by the magnitude, the size of the point. It gets smaller, that's right. Yeah, because we're dividing by the magnitude. And what it's pointing outwards because they're all positive. So I would not expect you to do this by hand. For plotting vector fields in R3, good to learn in R2, sure, and get an idea of how to do it. But definitely go to. You can have some really cool pictures online of these things. So I'm going to share a different. Let's see, application window, Chrome tab, vector fields, share. So remember that the gradient, what does the gradient do? What is it? The gradient at a point is the direction of steepest ascent. And the gradient is perpendicular to the level surface or curve. If you have a function mapping R3 to R, you calculate the gradient points in the direction of steepest descent, and it also is normal. It's perpendicular to the level surface. If it was f maps R2 to R, this is not working. Here we go. Okay, share. If it was R2 to R, then it would be perpendicular to the level curve. Let me share this. Cool. So this was a vector field that we just plotted, or we just calculated, the gradient vector field we just calculated. That's what it looks like. You see, you were correct. As we get further away, these vectors get smaller. Now, I think, as a matter of fact, if these were negative, these were all negative, is this? Give me a physical interpretation of what this is. This is gravity. Yeah, you did it. Yeah, you guessed it. It's gravity. Yeah. So, and then, you know, there's this theorem that we're going to get to later on when we start doing the vector. This is the intro to vector calculus chapter 16. But we're going to do, yeah, I suppose it could. Like it would push away, right? We're going to find that when we have a vector field that is the gradient of a scalar function, that is, we can find a scalar function and then we take the gradient of a scalar function, and that gradient is a vector field. It's called a conservative vector field, and then it'll cut down calculations a lot on integrals in these vector fields. So that's all I got for today. Thanks for participating.